Hello, everybody. This is Mike Sadowski, the CPS Science Coordinator, and here is your science news for this week. This week, we are concentrating on some of the weird science that happened in 2020. It wasn't all COVID, and here's some of just the new discoveries that scientists made. In the first discovery, we have a caterpillar that recycles its heads. So caterpillars grow bigger and bigger, and eventually a caterpillar goes through metamorphosis and becomes a moth or a butterfly. In this one, this is called, been nicknamed the Mad Hatter Pillar, because what it does is as it grows, usually when a caterpillar, this particular caterpillar grows or some like it will molt its skin. In other words, it kind of sheds its skin and it tosses it out. So that's what this one does, but it does a very, very unique thing. And the Mad Caterpillar, the first 4 times that it sheds its skin, including all the skin around its head, it just discards it and it's gone. But starting on number 5 in beyond, it actually saves the skin or the molt of its head and it attaches that to its next head. And it keeps happening. So here you see the caterpillar, the caterpillar plus its last 4 heads. And they are just stacking up like a head statue, like a head totem pole or something like that. Scientists, don't know completely why it's doing this, but everything seems to happen for a reason because of evolution. What they have noticed is this caterpillar, when something threatens it, it actually can beat the thing that's threatening it with its old heads, kind of like a bat. And in addition to that, scientists think it probably makes it look larger and so a little bit more threatening to everything coming around. So this is a new way of recycling, the Mad Hatter Pillar. The next one, it turns out up until this year, we kind of thought humans were the only animals that actually keeps and domesticates pets. We have cats, we have fish, we have dogs. A lot of us have chickens, and then chickens aren't always for eggs. In many cases, they're pets. We have all kinds of pets and we've domesticated them. Well, it turns out the long-fin damselfish also keeps pets, and that was just discovered in 2020. And the pet it keeps is this tiny, tiny, just a couple millimeter long shrimp. Well, why on earth would it would the damselfish keep shrimp as a pet? That seems to make no real sense, although we keep pets, but for our enjoyment. Well, they keep pets actually for another reason. It turns out the algae are feeding through the stuff that their waste, the shrimp through their waste. So in other words, shrimp poop. They're shrimp pooping all their waste out on top of beds of algae that the shrimp are actually farming. So the shrimp are taking care of algae that their waste is then pooping out, fertilizing the algae. The damselfish want to eat that algae. That's what they eat. And the shrimp are making and farming that algae plot even better for them. Now, in turn, the damselfish will actually keep, and I have a graphic here to show you. So what you have here is that you have the damselfish in here, and you have these predators that really, really want to eat the shrimp. They don't eat algae. These two fish here, fish 1 and 2, they want to eat these shrimp. Well, the damselfish are patrolling this area around their algae so that the shrimp are safe. So it is a beneficial relationship for both of them. The shrimp get protection from the damselfish, but then the damselfish are given the extra algae, the extra great algae from the shrimp poop that comes down. Another discovery that was being made out in California is that these roly-polies kill, and they kill in large numbers. And most of you love roly-polies. It's like the first insect that you really loved as a kid, and you get close to it with your finger and it rolls up into a ball for protection. Well, it turns out roly-polies aren't intending to kill, but what's happened is they have killed huge amounts of populations of a already threatened trout in a river and streams out in California. Scientists had no idea why. They had no idea the roly-polies were doing this. And the roly-polies, again, are not doing any of this on purpose, but there is a big discovery here. What was happening is along these rivers, there has been a lot of industrial contamination. And the metal mercury, very tiny traces of mercury, which is incredibly poisonous, was in the soil. when the roly-polies were eating their food and eating the stuff in the soil, they were also taking in the very poisonous mercury. The mercury, while very poisonous to us and many other things, was not impacting the roly-polies, but it was building up in their system. And then if the roly-poly got too close to the river or the stream and fell in, the trout were then eating the roly-polies, and the mercury was extremely poisonous to that trout. So while that is bad for the trout, now scientists can know, okay, maybe how can we keep these roly-polies away just from the stream to help the trout? But even more importantly, can roly-polies in the future be used to help clean up contaminated sites? It's worth a shot, and we have other animals and plants that do something similar. And then finally, we have funny penguin poop. Well, what does that possibly mean? Well, penguins poop a lot. Birds just, that's what they do. And it turns out, and normally it makes no difference, but there were scientists up in the Arctic region that were studying a very large population of penguins that they actually put in a closed environment in what basically looked like a greenhouse. So you had hundreds of penguins in this greenhouse, so the air was not exchanging. Well, when the penguins pooped, it was some of the chemicals in the penguin poop was reacting with some of the chemicals and the compounds and the minerals in the soil, and it was making what's called nitrous oxide. Probably doesn't seem that great or that interesting. Well, until I tell you that nitrous oxide is actually laughing gas. And normally it doesn't matter. The wind whips that up and takes it away and there's no problem. But the entire greenhouse was being contaminated or filled up with large amounts of nitrous oxide. And it didn't take long, but for the first few days, the scientists were acting unexplainably weird and silly. Everything was funny to them. Everything that happened was hysterical. Kind of like maybe you do in class sometimes. Somebody does something a little bit silly, not really funny to adults, but it's really funny to you. Well, that's how the scientists were acting. Everything was hysterical. Well, they finally found out that they were being contaminated with this laughing gas. So that is our news for this week, and we will see you next week for some more interesting science news. Hello, and welcome to another edition of the CPS Science Show. I'm Mike Sadlowski, the CPS Science Coordinator, and today we're going to talk about physics. So we're going to learn about some potential energy, some kinetic energy, some momentum, some friction. We're going to learn about a lot of physics. So sit back, enjoy, and send us your questions. Okay, in this first demonstration, we're going to use what's called the Newton's Cradle. Newton was actually not invented by Isaac Newton, but it uses the Newton laws of motion and physics to kind of demonstrate some pretty cool things. So most of you have probably seen this, and just to show you, if I pull back one of these marbles, it's going to go back, and what seems like it's never going to stop, you obviously know it is going to stop, but we're going to talk about some physics of why. So let's stop this. We have two things called potential and kinetic energy. Potential is the easiest one to remember because potential means it could happen, but it's not necessarily happening yet. Okay, so if I pull this back, way back here, this marble that I'm holding has the potential to have energy to it, but it doesn't have any energy because it's not moving, it's not doing anything, but it certainly has the potential because if I let go, it's going to become energy. And the second I let go, it's going to start converting to what's called kinetic energy. Kinetic means to move. So kinetic energy is energy that is moving. We can see it by moving. So very easy. So right now, everything has zero kinetic energy and zero potential energy. However, if I pull this back here, we have 5 balls with zero kinetic energy, 4 balls with zero potential energy, but now we have this ball over here that I'm holding that has quite a bit of potential energy. When I drop this ball, it's going to come and it's going to hit into the steel ball, the other steel ball next to it. Believe it or not, the steel balls are elastic. Elastic means it will slightly deform when it's impacted. You may not think it's deforming, but in its tiny, tiny micrometers, tiny, we can't see it. But when this steel ball hits this steel ball here temporarily dents, but then springs back. And when it springs back, that is then sending the ball that this energy put into here into this ball. This one will then dent, spring back, send the energy to this one. This will dent and spring back, send the energy into this one. This one does not have anything to dent, so the energy just keeps flying out this way. And eventually, gravity is going to stop this. At one point, it's going to stop, and then it's going to reverse, come back. Now this one dents this one dents this one, dents, and then this one has nothing to dent, and it's going to come back. What's also very interesting about this is that whatever energy you have going in is exactly the same amount of energy you have going out. So if I pull one ball back, when I let go, how many balls do you think is going to go out the other side? One. But now, what happens if I take two of the steel balls? So now I got double the potential energy here, and I let it go. Whoops, I did not mean to do that. So I'm going to let two go. What's happening? Two balls are flying off the end because two balls worth of kinetic energy hit and sent that momentum the other way. And now, what if I did three? Pull this back, three balls. What's going to happen? It's going to be a little odd. It actually, the third ball from the first one switches because it had excess energy, and three balls are going to fly off each side. And finally, you probably predicted, so I am probably a little shaky in this video because I'm trying to hold this steady and video at the same time. All right, I'm going to pull four back just slightly, and now you have four going. Okay, now here's the interesting part. This ball here, energy, there's a law called conservation of energy. It means energy cannot be created or destroyed. The energy we have here will have to be transferred in some way to energy in something else. It doesn't just go away, and it doesn't just gain energy without taking it from somewhere else. So if I pull this ball back to here, when it goes through, it cannot, this ball, when it goes all the way this way, then reverses, this ball cannot go any higher than where I started. Otherwise, that would be creating energy, and we can't create energy. It also says energy cannot be destroyed. So watch carefully and see if you think that this ball flying off on the reverse rebound is going to go as high as it was when I started. It's not. And it's getting less and less each time. So pause for a second and talk with your teacher and try to decide, why is it stopping? Because I said energy cannot be created or destroyed, but yet it certainly looks like energy is being destroyed. So take a second to think about that. Okay, now that you've talked about it, let's think about other factors that are in play here. This Newton's cradle would never, ever, ever stop if we didn't have anything else affecting it, but we do. We have a couple different types of forces affecting it. One, why does the ball want to go down? What force is that? Well, it's gravity. Gravity's making this go down. So as I go and do this, the whole reason it's working is because of gravity, but also one of the reasons it's going to stop is because of gravity, because these, and that's just one part of the reason, these want to go down and they want to naturally sit there because of the gravity. But if nothing was taking that energy away, we still should be going forever. Well, what else is happening? We have air. We have an atmosphere. So as this ball is flying this way, it is encountering air pressure, which is just why when you run, you feel that air against your face is wind, even on a calm day. It's not wind. It's just you throwing yourself through that wall of atmosphere. Well, this ball is doing the same thing, and that energy is getting displaced through that air friction. It's slowing it down. So energy is not being destroyed. It's just converting, and friction is robbing some of that energy and putting it somewhere else. And that is why eventually it slows down. Now we can do something. Let me remove the Newton's cradle. We can do something very similar, but we don't have to have it hanging on wires. But this one's not going to be as fun. But if I take one marble, well, I have to have the other three together. There we go. If I take one marble and I roll it towards the other three, how many do you think are going to come flying off the other end? I think you're going to be right. The energy cannot be created or destroyed, so I throw one ball's worth of energy that way, and one ball has to go the other way. And, okay, that was a very weak roll, but you saw it, but let's do it again. Okay, and one went. Now if I bring it back and I do 2 balls, what do you think is going to happen? What is with me and rolling it weakly? Let's try that again. And there goes the 2. Now I can't do the trick with 3 and 4 because there's no string bringing, the gravity's not at play here, bringing it back. But just show you that we still have a conservation of energy there. Now I'm going to do something very, very different. So give me 1 second to change this setup. Kind of briefly, maybe a little, get a glimpse of what I'm doing. I'm taking the 1 track off. And I'm putting another track on with marbles, but this time some extremely strong magnets are also on there. And I just want to show you another demo that shows conservation of energy. Okay. All right, now you're going to need to watch this carefully because my setup time takes a little bit of time to redo. So I want you to see it the first time, or of course you can just rewind this video a little bit. What I have here is I have 2 very strong magnets and 3 steel balls. I have 2 more strong magnets, 3 steel balls, and I have 2 more strong magnets and 3 steel balls. I then have a lone steel ball here, and I'm going to put that steel ball over on the side. And I'm going to give it just a little roll. And I mean, it's not going to have much energy at all. And we're going to see what happens here. And I'm going to have to back this way off so you can see it. It's going to be interesting to reach and see it. I want you to see, remember, the amount of energy I put in should be about the amount of energy that comes out that last ball. Remember when I had trouble rolling those balls with any force earlier, it showed when I rolled them very slowly, the ball at the other end moved out very slowly. Same thing should happen here. If I throw the ball, the first steel ball at it, the other one should come out pretty quick. I am going to barely roll this, and I want to see if the same thing happens at the end. Ready? Watch carefully. Watch how slow I roll. Watch the other end, and then I would rewind this so you can see it a couple times. All right, slow roll. Now, what did you notice there? Take a second to talk to your teacher and see if you think that obeyed the law of conservation of energy. Okay, if you had some time to discuss that, you probably noticed that even though I rolled this ball very slowly towards this magnet, the ball that was here shot off the other side extremely quick. Somehow we violated the conservation of energy. Or did we? Here's the deal. What we're not, it looks like a big trick. It looks impossible. Can't do it. However, these very strong magnets, let me get this out, the 2, now you can tell definitely the things that aren't the steel balls, that these 2 magnets here, magnets have a magnetic field and they have an incredible amount of potential energy in them. It's like invisible potential energy. So as this ball was coming towards, you know what, maybe I can very quickly set this up for you because it didn't destroy itself very much, so hold on. It actually takes quite a bit of force for me to remove the balls from the other side of these strong magnets, but I can get it, I think. All right, good. We can see it one more time. As I slowly move this towards this magnet, what's happening here is the potential energy stored in these 2 magnets is then transferred to these marbles, to this marble, which transfers to this marble, which transfers to this marble. It cannot transfer, so it moves. It then transfers to this magnet and gains its potential energy, to this magnet, and it gains even more potential energy, then transfers to this ball, to this ball, to this ball. It then cannot transfer it anywhere else, so it moves even faster. Transfers and gains, transfers and gains, transfers, transfers, transfers. It cannot transfer, and so it moves with the collection of all of the previous potential energies. One more time. A very slow roll. And it shoots off that other end. All right, I hope that kind of helps you understand conservation of energy, but if not, I have one more demo that could actually put my face at a little risk if I don't do it right.
Oh, oh.
All right, for this demo, we're going to stick with our conservation of energy, momentum, potential and kinetic energy. What I have here is a kind of like it's a heavy ball. It's a miniature bowling ball, and it's hanging from the ceiling. And so this is like a pendulum, and a pendulum just goes back and forth. And if you probably already know that if we did not have air friction, or if we didn't have atmosphere, we would have no friction. And this would go, if it went to here, it would go back and it would come all the way to here, and it would never ever stop, except for also the force of gravity. So we have a couple things. We have gravity that's trying to yank this down, which right now it's stopped, and it's equal. The forces are equal. We have the force of the rope that's holding it to the ceiling. We have the force of gravity pulling it down. The two can't move, and so it's the same. When I move it, we have air friction now in play that's going to try to slow this down. And then we also have gravity pulling it down, which is going to let it rest here. Otherwise, if it wasn't for gravity and it was only air friction, this could just end up resting here. But gravity is going to push it there. Now, we want to go back to conservation of energy. So on conservation of energy, this one can make you a little nervous, even though I know how it's going to work. If I hold the bowling ball, and I'm going to put my back and head against this wall so I don't cheat or make it worse for me. If I take the bowling ball right up to my nose and I let go, and I simply let go, you have the force of gravity, you have the force, you got, right now we have all potential energy, no kinetic energy. As soon as I let it go, that potential energy starts converting to kinetic energy. And it should come all the way back to just about my nose and no closer. I also know it's not going to give me a bloody nose because it shouldn't be hitting me in my nose. So let's take a look. Ready? It's touching my nose right now. There it goes. And I actually flinched because it's so close. I'm going to do it one more time, and I want you to see, it started with touching my nose. How close did it get? I'm going to try to close my eyes so I don't flinch. All right, I felt that. It came close. I felt the air. Why did it not hit my nose? It came so close that I felt that breeze. Again, air friction and gravity are trying to push this or slow this down a little bit. However, our potential energy going to kinetic energy, our conservation of momentum is going to keep this thing going for a while because air friction's not that big. So that pendulum's going to swing for a bit. All right, we will see you again next week for another science show. Have a great week.